Hi folks, happy storm day. Today we're going to look at some more tangent slopes and one application of them. In the video description below and on Google Classroom, you'll find a link to the full filled in notes, to the textbook section that we're working on, which is 2.4, and also a link to a review video for the whole chapter and a review sheet for the whole chapter. So right now we've been talking about secants and tangents. We defined a secant and a tangent. We looked at trying to approximate using numbers. We went ahead and developed this formula for the slope of a tangent. And that was really the big goal of the chapter or of the section so far. Okay, after that, we did some examples. So we found some slopes using this formula. There's another one. Then we actually found the equation of a tangent. So that was using the point slope formula. And that's really where we left it at yesterday. So the things that were assigned were page 93, 9 to 12, and finding the slopes and equations of tangents and normals for 4 different functions. We're going to pick up today looking at the slope at a general point. So let's imagine here that we had this function, root x plus 1, and we wanted to find the slope at a bunch of points. That would probably mean that we'd have to sub in one point, do the whole lim as h goes to 0 thing, sub in another point, do the whole lim as h goes to 0 thing, and again and again. What might be slicker would be to find an expression for the slope of this function anywhere. So that's what we're going to do here. We're going to use a general point A and figure out an expression for the slope anywhere. So let's just refresh our memories. The slope of the tangent at x equals a, where a is just some point that we care about, is the lim as h goes to 0 of f of a plus h minus f of a all over h. Really just rise over run with infinitely small run. So here, if I want to use this function, it's actually a little bit easier. All I need to do is figure out f of a and f of a plus h. So f of a would be, let me just sub in a for x. I'd get root a plus 1. What's confusing about this is the idea that we haven't subbed in a specific point, but we have subbed in some value that's going to represent our point, some point a. And if I go a plus h, f of a plus h, that would be a plus h plus 1. Okay, now I can go ahead and find this tangent. So let's pick a color here. So the slope of the tangent at x equals a is going to be lim as h goes to 0 of f of a plus h. Let me get that in the correct color. F of a plus h minus f of a. And we'll go ahead and sub in what those are. So lim as h goes to 0 of, this is all over h, square root of a plus h plus 1 minus the square root of a plus 1. This is what's going to help us find the slope of the tangent anywhere. Now you can see the problem that's going to happen here. We have radicals, so we're going to need to use conjugates. Okay, so I'm going to need to multiply by the conjugate of this whole thing, which would be root a plus h plus 1 plus root a plus 1 on the top and on the bottom. And we'll multiply through. And it looks bad, but it's actually not that bad. If I go root a plus h plus 1 times itself, I'm just going to get a plus h plus 1. The square roots, when they're multiplied by themselves, kind of undo each other. Now we're going to subtract whatever root a plus 1 times root a plus 1 is, which is just a plus 1. Now careful here, we're subtracting the whole thing, So it should really go in brackets. On the bottom, though, I still have, and I'll do it in the correct color here, I still have that green part, the root a plus h plus 1 plus root a plus 1. And if you hear noises in the background, that's my kids. Lim as h goes to 0. All right, let's see what happens. I'm just going to simplify this. So I have a plus h plus 1. Get rid of those brackets. Minus a minus 1 all over h by root a plus h plus 1 plus root a plus 1. Okay, you can see on the top, a minus a, that's going to go to 0. 1 minus 1 is going to go to 0. So I'm just going to be left with h on the top. So I have h all over h by this whole mess. And at this point, we can divide some stuff out. H's divide out. I get a little nicer limit. So we're still getting a little bit upset here that there are no numbers involved, really. There's still these a's. But a is just a placeholder for a number we can put in later, so that if we wanted to find the slope at a bunch of spots, we could then insert the number at the end. At this point, you can actually sub in. So that would be the square root of a plus 0 plus 1 plus square root of a plus 1, all on the bottom. Or that's root a plus 1 plus root a plus 1. Or in other words, on the bottom, 2 of those root a plus 1s. Okay, they're like terms. This is the slope at any x value, x equal to a. So if I wanted to find the slope at 1, now I just put 1 in for a, and I'd get 1 over 2 root 2. If I wanted to find the slope at 3, I'd put 3 in for a. So the actual work of finding this slope over here was a little more painstaking when we had all the variables. But at the end, it's more useful because it lets you find slopes at different points without having to go through all this misery again and again. So that's essentially finding slope at a general point. We use the formula, but without putting in a specific x value. The other example we're going to look at today is an application. So we're going to imagine that we go for a field trip on Jupiter's moon, Europa. And there's this formula for the distance fallen in feet by an object on Europa. Now, this is going to be different on different celestial bodies, on different planets, because the acceleration due to gravity is different on different planets due to the mass of the planet. So here it works out to be this nice coefficient 2t squared. That's the distance fallen in feet after t seconds. And it asks us for two things here. It asks us for the average speed over the first 3 seconds. Okay, average speed. Average speed should make us think of the slope of the secant if you're looking for average rate of change. So average rate of change means secant, or secant slope. Now here it happens to be not that bad for us to graph it, so let's do that. Okay. And we'd get a parabola that looks like this, okay, where this is the distance fallen in feet, and this is time in seconds. Okay. And obviously after 0 seconds, it's fallen 0 feet. If I subbed into this formula, 0, I'd get 0. If I put in 3 seconds, let's see, that would give me 2 times 3 squared, or 18 feet. If we did this on Earth, in 3 seconds it would have fallen further. And if we want the average rate of change, then we're looking for the slope of this secant. So average rate of change is just change in y over change in x, or y2 minus y1 all over x2 minus x1. Okay, and I can label these x1, y1, x2, y2. So that's going to give us 18 minus 0 all over 3 minus 0, or 18 over 3, or 6, which really means nothing until we insert the units in there. 18 what? 18 feet over 3 what? 3 seconds. So that's 18 feet per 3 seconds, or an average speed of 6 feet per second over those first 3 seconds. But you know from watching something drop, it doesn't fall at a constant speed. That's just an average. So what we might be interested in is the exact speed of the object 3 seconds after it's dropped. So that brings us to part B. Find the speed of the object exactly 3 seconds after it was dropped. If it's at a point, this is where we're talking about the slope of a tangent. Okay, so let me zoom in here. I'm going to draw in that tangent. I'm really interested in this slope right here. Okay. So that would be slope of the tangent at x equals 3. And of course, we're going to develop some better notation for this. But I want it to be really clear that when we use this limit formula, it's because we're looking for a tangent slope. Okay. So I could change this formula to look like this. d of t equals 2t squared. When we look for that tangent slope, we're looking for lim as h goes to 0 of d of 3 plus h minus d of 3 all over h. So this time it's at a specific point. We don't need to do that general point stuff we did in the last example, though we could, and then sub in at the end. Let's see what we get. First of all, we need to go off to the side and figure out what d of 3 is. So maybe I'll use some different colors here. d of 3 is pretty straightforward. That's 2 times 3 squared, or 18. We actually already knew that over here. So if I rewrite this thing, that'll give us lim as h goes to 0 of, this is over h. I'm going to have a minus 18 at the end. I also need to figure out what d of 3 plus h is. So that's going to take a little more doing. So maybe I'll do that up top here. I want to figure out d of 3 plus h. I'm just doing this off to the side so that I don't have to do it within the limit formula. So that's 2 times, if I go 3 plus h times 3 plus h, I'm going to get 9 plus 6h plus h squared, just foiling out those things, or 18 plus 12h plus 2h squared. Great. That's going to sub in for d of 3 plus h. So I'll get 18 plus 12h plus 2h squared. Now it's really just running through this limit. So I'll have lim as h goes to 0 of, let's see, those 18s are going to subtract off. So I'll have 12h plus 2h squared all over h. It's up to you at this point whether you want to take out 2h or just h. I'm just going to take out h because that's really all I want to divide out. But the math will stay the same either way. The result will be identical. Okay, so now we're in this great position where we can divide out h, and the sleight of hand of limits is that we can divide it out because h goes to 0, or h approaches 0, but it is not actually 0. Sneaky, hey? And then we're going to head down here, and we're going to be in a situation where we can evaluate. We're going to have 12 plus 2h. As h goes to 0, this is the point where we say, h is approaching 0. All right, well, it's basically 0 then. And that gives us 12 feet per second, which is no big surprise. If we look at that tangent line, it looks steeper than the secant that we drew. So we have found an instantaneous speed. Now that in turn leads us to some practice. Last night's practice was this stuff, page 92 and 93, 9 to 12. So if you didn't get a chance to do that, you might want to look at that. The stuff that relates to what we did today is over here. If you're looking for a little more practice on finding the equations of tangents and normals, here are a couple right here. And here are the alleged answers to those. I guess lastly, I'll just use the last few minutes of this video to put up on the screen these questions from the textbook, so that if you forgot your textbook and don't want to download the PDF, then they'll be right here. But of course, the PDF is linked in the video description below. A couple of other things to mention are that there is a review sheet of the whole chapter linked below. There's also a concept roundup video linked below for the whole chapter if you feel like you need to take a look at some concepts again. And we're looking at our test on Wednesday. Okay. So the test is going to be what the assignment contained, plus this new stuff on finding slopes. We'll get our assignments back on Monday, and we'll go over them then. All right, so here come the questions from the textbook. Here were the ones from last night, 9 to 12. You can pause if you want to take a look. Here come the ones from today. We're doing just part A of these. So finding the slope at a point x equals a, so the general point on these ones. And then the ones that we're talking about speed are these. So find the instantaneous rate of a function in feet per second. That just means find the speed. And this. And this. Oh, and we could do this one as well. Okay. So again, you can pause if you want to look at those. And the answers would be in the PDF. All right, folks, take care and good luck with the material. I'll see you Monday.